Look at this code for a second. Two threads, T1 and T2, both incrementing the same counter. Both incrementing the same counter. Simple question, what will this print? Let's see the output once. If you see the output, we are expecting the 2 lakhs is the count, but the actual count was less than this 2 lakh. So when two threads are incrementing the number, but the count is mismatching. So there is a data inconsistency here. And here is the shocking part. The variable is volatile. Even we used volatile, why it is went wrong? This is one of the most misunderstood concepts in Java concurrency. Volatile is not atomic, synchronized is not always the best choice, and atomic integer works in a completely different way. In this video, I will show you what volatile actually guarantees, why counter increments breaks, how synchronized fixes it, how atomic integer works, and exactly when to use each one in real system. To understand this problem, you need to understand how CPUs actually work, because the bug is not in Java. It is in how hardware behaves. Modern CPUs don't read from main memory every time. That would be too slow. So each CPU core has its own local cache. Think of it like this. Main memory is the source of truth. Each thread working on its own cached copy. Thread 1 reads count as 0 and stores it in its own cache. Thread 2 also reads count as 0 and stores it in its own cache. Now both think the value is 0 and both increment, both write back. One update is lost. So there are actually two different problems here. One is visibility. Can one thread see another thread's change? Atomicity. Is an operation indivisible? Volatile solves visibility only. Synchronized solves both. This is the foundation of everything. So you understood now, right? So we have two problems when multi-threading is happening. One is visibility, like one thread writes something, it should appear to the other thread, but it is not happening because they have their own individual caches, that is local caches. They are reading it from their local cache, right? Another one is atomicity. It is an operation indivisible, like two threads are doing the operation at same time and there is a race condition and there is a data inconsistency issue, right? We'll see how volatile will solve this problem. So we already seen that without volatile, each thread reading it's from its own cache, right? With volatile, now volatile does exactly two things here, nothing more, nothing less. Every write immediately goes to main memory. Every read always comes from main memory. So yes, visibility is guaranteed now, but atomicity not guaranteed. Let's break the counter functionality. What went wrong, we will see that. Let's break the counter functionality here. It looks like one operation, but it's actually three steps: read, add, write. Here thread 1 reads count as 5. Thread 2 also reads count as 5. Thread 1 writes incrementing the number as 6. Thread 2 also writes the number incremented as 6. The final value is 6, but we are expected 7, right? Volatile made sure both threads saw latest value, but it did not stop them from interfering. You understand, right? So both threads are writing at the same time. They're able to see the changed value, but they're writing at the same time. That's where the data inconsistency, it's a race condition is happening. So now the question is when to use volatile. The rule is very simple. One thread writes, multiple threads read. No read, modify, write. Here is a simple example. Shutdown flag is the classic example here. Here is what's happening. One thread updates running as false. All worker threads are continuously reading it. Because it's volatile, the moment we set it to false, all threads immediately see it and they stop safely. No race condition, no incorrect behavior. And also another example, which is configuration refresh. In real systems, configuration gets updated at runtime. One thread updates the config, multiple threads read it. No modification, only read access. Perfect use case for volatile. So now you understood, right? When not to use volatile, that is clear. You have to avoid if you have any increment, decrement, add, update based on concurrent value, do not use volatile because those are read, modify, write operations and volatile cannot make them safe. So in simple, you need to remember volatile is for only visibility, not for atomicity. And the safest mental model is one writes, many read. Now that we understand the problem, let's fix it. We saw that volatile gives only visibility, but it does not prevent two threads from interfering. So the next question is, how do we make the entire operation safe? That's where synchronized comes in. Think of synchronized like a room with a lock. Only one thread can enter at a time. If one thread is inside, all other threads must wait. Now we'll see our counter increment problem. How synchronization will. So here thread 1 enters increment. It acquires the lock. It reads the count as 5 and adds 1 which is 6 and writes back to main memory. Then release the lock. Now thread 2 enters. It reads the original value as 6. Now thread 2 enters. It reads the updated value as 6. Then it will add 1 which is 7 and it will write back. So the final result is correct. So synchronized does two things at the same time. It ensures only one thread execute the block. It ensures all changes are visible to others. So it solves atomicity visibility. Let me show you the code. So here is the synchronization example, how we can use it. Basically same two threads, which is incrementing the number. And if you see the counter increment, we have applied synchronized for that method. It means the thread enters to this method, it will log this operation so that other threads will wait outside. Right? This is how we can solve that atomicity and visibility issue with the synchronized. Now here is where things get interesting. Synchronized is safe, but it comes with a cost. Imagine a real system. There is a 500 threads all trying to update the same object. What happens? All threads line up waiting for the same lock. Only one thread runs, others are blocked. And here is the expensive part. The OS suspends waiting threads, later wakes them up. This is called a context switch and it's not cheap. In high traffic system, this becomes a bottleneck. CPU usage increases, throughput drops, latency increases. system slows down even though logic is correct. There is another mistake many developers make. They synchronize only the write, but not the read. Here, if you see, only the write operation we are synchronized, but read not synchronized. This code looks fine, but it's not. Why? Because get is not synchronized here. It may read a stale value from cache. So you have to synchronize both write and read operations. If multiple threads read and write a shared variable, all access must be synchronized on the same lock. Think of synchronized as one thread at a time. Everything inside is safe. In summary, if you need multiple operations to behave as one, strong consistency, guaranteed correctness, use synchronized. But remember, it blocks threads, doesn't scale well under heavy contention. So far, we have seen two approaches: volatile, which is fast but unsafe for counter updates; synchronized, which is safe but can block threads. Now the question is, can we get both safety and performance in terms of counter increment? Yes, exactly what AtomicInteger gives us. AtomicInteger solves the counter problem without using locks. No synchronized, no blocking, no waiting. So how does it work? It uses a concept called compare and swap, which is CAS. Think of CAS like this. You tell the CPU, if the value is still 5, change it to 6. If still 5, update happens. If someone already changed it, do nothing. That's it. No lock, no waiting. This looks simple on the outside, but internally something very powerful is happening. Let's break it down. Thread 1 reads the value as 5. Thread 2 also reads the value as a 5. Thread 2 also reads the value as 5. Thread 1 tries, if value is 5, make it 6. Success. Then thread 2 also tries, if value is 5, make it 6. But it fails because now the value is already 6. So what does thread 2 do? Retries. Reads again the value. Then it will get updated value as a 6. Then it tries. Then it make it as a 7. So now the success. Final result is correct value. So instead of blocking, threads compete. One wins, others retry. No threads is ever suspended. So AtomicInteger is lock free but still thread safe. So why is this faster than synchronized? Because no context switching is happening, no thread blocking, no OS involvement. Everything happens at CPU level. But there is one trade-off. CAS is not magic. Under low contention, almost always succeeds very fast. But under high contention, many threads fail CAS, many retries happen, still faster than locks, but not always perfect. In real world usage, AtomicInteger is widely used in real systems, where request counter, which is safe, fast and no locking. And the another example, rate limiter. So when you want to use in APIs, limits request safely, you can use for this. Let me show you the code. So here we have used AtomicInteger. And in the counter increment, we have used count, increment and get. So now see the output here. So expected count, actual count, which is same, right? So the AtomicInteger is safe, no locking. Now we have seen all the tools individually: volatile, synchronized, AtomicInteger. But in an interview or in real production, you won't be asked to explain them separately. You will be asked which one would you use and why. So let's simplify everything into one clear mental model. All of these tools solve concurrency issue, but they solve different problems. Let's break it down step by step. The visibility problem. First question is visibility. Do you only need visibility? Means one thread writes, others just read. Then use volatile. No locking, no overhead, just fresh values. Atomicity. Do you need multiple operations to behave as one? Like transfer money, update multiple fields, execute a sequence safety. Then use synchronized because only one thread executes at a time. Now another case, you have a single value, multiple threads update it like a counter. Then synchronized works, but it blocks other threads. So instead of, you can use atomic integer because it's lock free, it uses cache much faster under normal load. So here I have listed the top 5 interview questions. You can pause for a minute, read question and answers. You always remember the 6 points regarding volatile, synchronized, atomic integer. Thanks for watching GK TechVerse. Subscribe and keep upgrading your skills. See you in the next video.